Let me introduce you briefly. So hello everyone, welcome. It's my great pleasure to introduce Professor Vladimir Peller from Michigan State University, who will speak on the functions of perturbed commuting dissipative operators.
Thank you very much. Thank you very much. I'm sorry. I'm sorry for the late start of the talk. Okay. So I'm going to speak about estimates of functions of perturbed operators. Let me first remind early results. Suppose we have. Let's start with the case of self-adjoint operator. Suppose we have a self-adjoint operator, say A, and we consider its perturbation, say B. It's also self-adjoint. A is self-adjoint and B is also self-adjoint. And suppose that we know that the operator B minus A is small in a certain sense. There are many possibilities to measure the size of B minus A. You can take the operator norm, you can take the, say, trace class norm or Schadenfreude Neumann norms. And if f is a function on the real line, we are going to consider only continuous functions that takes complex values. We can consider the function of this operator f of A and compare it with the function of the operator B. And well, then the problem is to estimate the size of f of B minus f of A in terms of the size of B minus A. In particular, we can consider the following natural class of functions called operator Ellipses functions. This means that the norm of f of B minus f of A is less than or equal to constant times the norm of B minus A. Such functions are called operator Ellipses functions. Well, let me use the notation OL of R is the class of all operator Ellipses functions. First of all, it is absolutely trivial that if f is operator Ellipses, then f is Lipschitz, which means that modulus f of x minus f of y is less than or equal to constant times modulus x minus y. Okay, for several years, it was unknown whether the converse is true. Actually, for many years, it was unknown whether the converse is true. And the first, it turned out that the converse is false. If f is a Lipschitz function, then it is not necessarily true that f is operator Lipschitz. And the first example was constructed by Farfarovskaya. Well, and then the problem was which actually functions are operator Lipschitz. It turned out that this class of functions has many peculiar properties. For example, if f is operator Lipschitz, then f is differentiable everywhere on the real line. However, it is not true that f must be continuously differentiable. And in particular, it follows from the differentiability that the function modulus x is not operator Ellipses. And moreover, if we change the function modulus x in a neighborhood of 0 and make it smooth, this function is not operator Ellipses. It doesn't help. Because if f is operator Ellipses, then the limit I'm sorry. Can you hear me?
Yes, perfectly.
Yes, we can.
Okay. Then the limit of f of x over x exists as modulus x goes to infinity. And so even if we change the function modulus x in a neighborhood of the origin, still the resulting function is not operator Ellipses. And this fact that operator Ellipses functions are necessarily differentiable everywhere was proved by Johnson and Williams. And Kissin and Schulman proved that the function x squared sine 1 over x is operator Ellipses. Though it is not continuously differentiable. The derivative is not continuous at the origin. Okay. As for sufficient conditions, I can mention my result of 1985 that if f belongs to the base of space B infinity 1, 1 on the real line, then f is operator Ellipses. And let me say a few words what we mean by this base of space. Okay, this means actually that f can be represented. This condition is slightly stronger than Lipschitzness. If f can be represented in the form the sum of fn, where the function fn has Fourier transform supported, say, in minus 2 to the n, 2 to the n, and the sum of the Lipschitz norm actually of the function fn is finite. There are many possible descriptions of this base of space. So if it's slightly, this condition is slightly stronger than the Lipschitz condition. The Lipschitz condition means that the derivative has finite real infinity norm. And this Besser condition assumes that we can actually expand f in a series with such a localization property for the Fourier transform, such that the sum of the Lipschitz norms is finite. Okay, then, okay, today I'm going to consider the case of dissipative operators. Let me first mention that similar results also hold for unitary operators. And for contractions, which means that the norm of the operator is less than or equal to 1. And today I'm going to speak about joint results, recent joint results with Alexey Alexandrov. I am going to consider the case of dissipative operators. Let me remind that an operator is called dissipative if the imaginary part of the inner product of Lx, L is dissipative, Lx x is non-negative. Actually, in applications, it is important to consider not necessarily bounded dissipative operators, but also unbounded. This means that L is densely defined. And this inequality holds for all vectors in the domain of the operator L. dl is the domain of the operator L. Okay, then it is also natural to consider the class of maximal dissipative operators. We are going to consider only maximal dissipative operators, which means that if L has an extension, say L1, which is also dissipative, what do we mean by an extension? It means that we can enlarge the domain of the operator L. So if it has a dissipative extension, then L must be equal to L1. Such dissipative operators are called maximal dissipative operators. And there is a one-to-one correspondence between maximal dissipative operators and contractions T has norm less than 1, such that 1 is not an eigenvalue. Of T. Namely, if T is such an operator, then we can define the following dissipative operator. L is I times the identity plus T times the identity minus T inverse. This is a densely defined operator, and it is maximal dissipative. And the operator T can be obtained from L by the following formula. And well, so there is a one-to-one correspondence between all maximal dissipative operators and all contractions for which 1 is not an eigenvalue. And many problems actually can be, for dissipative operators, can be deduced to the corresponding problems for contractions. But actually not all the problems. And the problem I am going to consider today is not of this kind. The corresponding problem for contractions is much easier. First of all, how can we define functions of dissipative operator. Suppose that L is maximal dissipative operator. Which functions can we consider? Okay, we can proceed from L to T, where T is the corresponding contraction. It's called the Cayley transform. And for contractions, we can define functions of contractions the following way. First of all, T has a unitary dilation. And what is that? It's a unitary. This is the theorem by Selfadjoint. This means that there exists, if T is an operator on a Hilbert space H, so there exists a bigger Hilbert space K and a unitary operator U on K, such that the powers of T can be obtained from the powers of U in the following way. We can see the powers of U, restrict them to the subspace H and take the orthogonal projection to H. And this is true for all n greater than or equal to 0. Okay, then we can define functions of T in the following way. It's the projection onto H times G of U, where U is our unitary dilation, restricted to H. And this can be done for all functions. G is in H infinity, it's a bounded analytic function in the disk, and G is continuous everywhere on the unit circle, except possibly at 1, at the point 1. Then we can consider such a functional calculus, and the von Neumann inequality says that the norm of G of T is less than or equal to the H infinity norm of G. Okay, how can this help us to define functions of dissipative operators? We can see the class, say, CA infinity. It's the set of all functions F in H infinity on the upper half plane, such that F is continuous on the real line. Then, if F belongs to this class, then we put F of L is, by definition, we can see the conformal actually map omega from the unit disk to the upper half plane, and can see the composed function f of omega and apply it to the contraction T, where T is the Cayley transform of L. Well, let me remind that omega of zeta is by definition I times 1 plus zeta divided by 1 minus zeta. Okay, this is the way we can define such functions. But actually, and if you can see the base of okay, we can consider the base of space B infinity 1, 1. The unit disk, it's the base of class of functions in the unit circle that extend analytically to the unit disk. And this is this class consists of is contained in the disk algebra. So it consists of continuous functions on the unit disk that are analytic in the unit circle that are analytic in the unit disk. However, if you define the Bezier space on the upper half plane, actually it contains unbounded functions. So when with this definition, actually we cannot use arbitrary Bezier functions because they can be unbounded, and we defined functions of contractions only for bounded functions. So we can actually extend this definition to the case when the function is not necessarily bounded. We can see the following class: z plus I times Ca infinity, where class Ca infinity was defined here. So we can multiply such functions by the function z plus I, and certainly we can get unbounded functions. So if f belongs to this class, then we can represent f in the following way: f of zeta is equal to fi of zeta times zeta plus I to the minus 1, where fi of zeta is f of zeta divided by zeta plus I. And then we can define the operator f of L for such functions, for functions in this class, which contains unbounded functions. F of L is by definition L plus I times fi of L. Let me observe that fi is a bounded function and it belongs to Ca infinity. So there is no problem to define fi of L. It is a bounded linear operator, but the operator L plus I can be unbounded. And so how to define this operator? It is a densely defined operator, and its domain consists of those vectors x for which fi of L x belongs to the domain of L. Then we can define f of L on a dense subset, and actually this class contains the Bezier class of analytic function b infinity 1 1 of C plus means that they are analytic. Or actually, there is no need. Okay, it's of C plus. So we can. This definition allows us to define functions of dissipative operators, functions f of L for arbitrary function that is in the Bezier space b infinity 1 1, and it is analytic in the upper half plane. And such operators are in general densely defined. Then we consider a similar problem. We consider the problem of operator Ellipses. So suppose that f belongs to this class, this Bezier class of consists of functions analytic in the upper half plane. And the question is whether it is true that f of L1 minus f of L2 has norm less than or equal to a constant times the norm of f of times, excuse me, the norm of L1 minus L2. So whether it is operator Ellipses in this sense, is this true or not? And the main result, our work is that this is true. However, the proof is considerably more complicated than in the case of Selfadjoint operators, in the case of unitary operators, in the case of contractions. Well, okay. Let me first explain why this fact is considerably more complicated. Let me give a brief idea how to prove a similar result for self-adjoint or unitary operators or even for contractions. Okay, suppose that A and B are, say, let me assume for simplicity that they are bounded self-adjoint operators, though the fact holds also for unbounded self-adjoint operators. And F is in the Bezier space B infinity 1. Then we want to consider F of A minus F of B. Okay, the idea actually uses a formula by Daletsky and Crane, and also the theory of double operator integrals by Biermann and Selamek. Okay, let me first give a brief introduction to double operator integrals. Okay, what is that? It's an expression of the following form. Where E1 and E2 are spectral measures, on Hilbert space. Phi is a bounded measurable function, and Q is a linear operator, say bounded linear operator. And the problem is how to interpret what we mean by this double operator integral. And the idea by Biermann and Selamek was first to consider the case when Q is a Hilbert-Schmidt operator. In other words, Q belongs to the class S2, which is the class of Hilbert-Schmidt operators. Then we can consider the following auxiliary spectral measure. But it's not a spectral measure on the initial Hilbert space. It's the spectral measure on the Hilbert-Schmidt class S2. It is defined in the following way. We can define it on measurable rectangles by the equality. We consider a measurable rectangle delta cross lambda, and we apply it to an operator Q, which is a vector in the Hilbert-Schmidt class S2. Then it's defined in the following way. It's E1 of delta, Q, E2 of lambda. Then it can be shown that it extends to a spectral measure and we define the double operator integral as the integral of the function phi with respect to the induced spectral measure E, which we have just defined. So this is a bounded linear operator on S2, and we apply it to the operator Q, which is a vector in S2. And with this definition, it is clear that the Hilbert-Schmidt norm of the double operator integral is less than or equal to a constant. The Hilbert-Schmidt norm is less than or equal to the L infinity norm of phi times the Hilbert-Schmidt norm of Q. Okay, but this is only in the case, everything is very nice, only in the case when Q is a Hilbert-Schmidt operator. What happens if Q is an arbitrary bounded linear operator? In this case, we cannot define such double operator integrals for arbitrary bounded measurable functions phi. We have to impose additional assumptions on phi. Okay. Let me do it. First of all, we can consider only those functions phi for which the following implication holds. If Q is a trace class operator, let me remind that it is a subset of the Hilbert-Schmidt class, then the double operator integral also belongs to trace class. This is not true for all functions phi, but for certain functions this is true. And we call such functions phi is a Schur multiplier of S1. It's called a Schur multiplier of S1. Okay, then for such functions phi, we can define double operator integrals if Q is a trace class operator. And by duality, we can define also such double operator integrals for arbitrary bounded linear operators Q. I mean, if phi is a Schur multiplier of S1. And then we have the following inequality, the integral double operator integral dE1 Q dE2, the norm is less than or equal to the norm of phi in the space of Schur multipliers times the norm of Q times the constant operator norm. So if Q is a, if phi is a Schur multiplier, let me use the notation as M of E1, E2. If phi is a Schur multiplier, then we can define double operator integrals for all bounded linear operators. Okay, how is this related to our Ellipses type estimates? Okay, we have the following formula: f of A minus f of B is the following double operator integral: f of S minus f of T over S minus T. Then we have dEA of S, A minus B, and dEB, dEA S times A minus B dEB of T, where EA is the spectral measure of A, excuse me, something is wrong here, dEB. And EB is the spectral measure of B. Okay. Actually, it turns out that this formula holds. This is true if f of s minus f of t over s minus t is a Schur multiplier. Is a Schur multiplier actually with respect to all possible spectral measures. And this was observed by Bierman and Solomek. Okay, then if in this case, then f is operator Lipschitz. Why? Simply, we have the following. The norm of f of a minus f of b. If you use this inequality, we are going to use this inequality, is less than or equal to the norm of this divided difference. In the space of Schur multipliers times the norm of a minus b. So f is operator Lipschitz. Okay, now I would like to briefly discuss why this formula holds. Simply, okay, we have the following integral of f of s minus f of t divided by s minus t dE a of s a minus b dEb of t. Actually, when we integrate, then a can be replaced with multiplication by s, because here we have the spectral measure of a, and a is equal to the integral of s dEA of s. So we can replace a with s and b with t. After we replace a with s and b with t, we have a cancellation. Here we have s minus t, and here we also have s minus t. So we get the following integral of f of s dEA of s dEb of t minus the integral of f of t dEA of s dEb of t. Okay, the first integral is equal to f of a, and the second integral is equal to f of b. Okay. Actually, this is a rigorous proof if f is a bounded function also. If f is also a bounded function. If f is unbounded, then the proof is slightly more complicated. This is an idea why, actually we can use double operator integrals and how this can lead to Lipschitz type estimates. Okay, then I mentioned that in 1985, I proved that if you consider Bessa spaces, such Bessa spaces, then if f is such a Bessa function, then f is operator Lipschitz. Okay, the idea is the following: we can represent f as the sum of the functions fn, such that fn has Fourier transform supported in the interval minus 2 to the n, 2 to the n. And then I proved that in this case, Fn of S minus Fn of T has the following estimate of Schur multiplier norms. Is less than or equal to a constant times 2 to the n times the L infinity norm of F. And then this estimate just leads to the fact that if F is a Bessel function, then it is operator Ellipses. Okay, this is for self-adjoint operators. Okay, then for unitary operators, actually, the situation is even easier than for self-adjoint operators, because all Bessel functions are actually continuous in the closed unit disk, and we don't have problems with unbounded functions. Also for self-adjoint operators, the same result holds for unbounded self-adjoint operators, but for unitary operators, we do not have unbounded unitary operators. So for unitary operators, the situation is even easier. Several years ago, I proved similar results for functions of contractions. If T is a contraction and F is analytic in the Bessel space, then the norm of F of T1 minus F of T2 is less than or equal to a constant times the norm of T1 minus T2. Well, what is the difference? How the above reasoning can be adjusted to the case of contractions? We cannot represent T as an integral of a function of, with respect to a spectral measure. But we can consider, instead, we can consider semispectral measure. So what is the difference between semispectral measures and spectral measures? If E is a spectral measure, then E of delta, if delta is a barrel set, then it is an orthogonal projection. And if we have a semispectral measure, if say E is a semispectral measure, then E of delta is a self-adjoint operator that is less than or equal to the identity operator and greater than or equal to 0. So it's a more general, and it is also sigma additive in the strong operator topology. And then we can define integrals with respect to semispectral measures. And in the case of contractions, each contraction T has a semispectral measure. Actually has a unique semispectral measure. On the unit circle, spectral measure say.
What do you mean by semispectral measure?
Can you speak louder, please?
What do you mean by semispectral measure?
A semispectral measure, it's a function that for each Borel set, it gives us a self-adjoint operator E of delta that satisfies this inequality, and also it is yeah,
got it. Thank you.
sigma additive in the strong operator topology.
Yeah,
so it's a more general notion than the notion of a spectral measure.
Okay, thank you.
It has a unique spectral measure, say ET, on the unit circle, and then F of T can be represented as the integral over the unit circle with respect to this semispectral measure. And this actually calculus that takes t to f of t is linear and multiplicative if f is analytic in the unit disk case, if f, say, is in the disk algebra. Then to prove that Besser functions analytic in the unit disk are operator Ellipses, so we want to prove this estimate for such functions f, we can use the same idea, but instead of considering spectral measures, we can consider semispectral measures. So we can write f of t1 minus f of t2 as the double operator integral f of zeta 1 minus f of zeta 2 over t1 minus over zeta 1 minus zeta 2 with respect to the semispectral measure det1 of zeta 1 times t1 minus t2 times det2 of zeta 2. It can be shown that if it actually suffices to prove this formula for very nice functions, say for analytic polynomials, and then the same reasoning shows that actually if f is a Besser function, then it is operator Ellipses in this sense that for all contractions we have such an estimate. Okay, however, in the case of dissipative operators, the situation is considerably more complicated. Suppose that L1 and L2 are maximal dissipative operators, then they also have semispectral measures. Say E1 and E2 are semispectral measures, which means the following, that f of L1 minus equals the integral of f of t d E1 of t for all functions f that are analytic in the upper half plane and continuous on the real line. But actually, such functions do not have to be bounded. They do not have to be bounded.
Sir,
Excuse me?
excuse me, sir. Sir, here this semispectral measure is corresponding to the contraction or what?
Okay, each contraction has a unique semispectral measure, and it is a semispectral measure on the unit circle, and each dissipative operator has a spectral measure, a unique semispectral measure on the real line. How to get it? We just take the Cayley transform, we get a contraction, and then we consider each semispectral measure on the unit circle, and then we use the conformal map omega to transfer the semispectral measure from the unit circle to the real line, and we get the semispectral measure of the dissipative operator. So each dissipative operator has a unique semispectral measure on the real line. But the difficulty is the following: that if we want to use, we want to prove this a similar formula: f of L1 minus f of L2 equals integral double operating integral of f of s minus f of t divided by s minus t de1 of s L1 minus L2 de2 of t. However, here, if f belongs to the Besser class, such operators do not have to be bounded. And actually, we cannot write that the integral of f of S1 minus f of S2 or S1 minus S2 L1 here dE1 L1 S L1 minus S2 minus L2 times dE2. Sorry, I'm sorry, there's a confusion. S f of S minus f of t S minus t. dE2 of t. We cannot replace L1 with S, and we can replace L2 with t, as we did in the case of self-adjoint operators, or we can do it with case, because S and t are unbounded functions. And to integrate, to consider double operator integrals, we can integrate only bounded functions. So this method does not work at all.
Professor Peller, you have about 5 minutes.
5 minutes. Okay. So this is so we have to actually to invent something quite different, and we did it. So we proved that if f belongs to the base of space, then it's true that f of L1 minus f of L2 is less than or equal to a constant times the norm of L1 minus L2. But actually, this is a much more complicated than in the case of contractions and the case of unitary operators. Okay, then I can also state analogs for of known results for self-adjoint operators. We proved this in my joint paper with Alexander. We proved these results for self-adjoint operators, but now I can state it for dissipative, for maximal dissipative operators. If f is a Hölder function, here alpha is between 0 and 1, analytic in the upper half plane, then the norm of f of L1 minus f of L2 is less than or equal to the constant times the norm of L1 minus L2 to the power alpha. So in here alpha must be less than 1, because if alpha is equal to 1, then it is not true that if we have a Ellipses function, it must be operator Ellipses. But if alpha is less than 1, then if we have a Hölder function, actually it is operator Hölder. So it's a big difference between the case of operator Ellipses function and the case of operator Hölder functions. And one more result I would like to state. Again, we proved this for self-adjoint operators in my joint paper with Alexander. If p is greater than 1, alpha is between 0 and 1, then if L1 minus L2 belongs to the Schatten von Neumann class SP, then f of L1 minus f of L2 belongs to the Schatten von Neumann class SP over alpha. And the norm of f of L1 minus f of L2 in the Schatten von Neumann norm SP over alpha is less than or equal to a constant times the norm of L1 minus L2 in the space SP to the power alpha. For p equal to 1, this is not true. Okay, thank you. Thank you. I can stop at this point.
Thank you very much. We have time for a couple of quick questions. So if you have a question, then please just go ahead and ask it, because I probably won't be able to see your raised hand.
Damir, there is a
Yeah,
question.
So there is a question in chat. How the results you stated depend on the class of operators you consider. For example, can we hope the equivalence between OLF and Ellipse to be true for a small class of operators? You can see it in chat.
Okay. Okay. In the case of self-adjoint operators, it suffices to consider only finite rank operators. And if we have such Ellipses, operator Ellipses inequalities for all finite rank operators, then we have for all finite rank self-adjoint operators, then we have the same inequality for arbitrary self-adjoint operators. It suffices to consider only finite rank operators.
Other questions?
Sir, when you define the functional calculus for contraction, that is GT is the compression of GU, and you take G as a H infinity function. Sir, if we take G as a continuous function, then what is the problem?
Excuse me, I have a problem. Your voice is breaking. Could you please repeat the question slowly?
Sir, when
Yes.
we defined functional calculus for contraction through this semispectral measure or compression of unitary operator, that at that time we take G as a H infinity function. So if we just take G as a L infinitive of or continuous function, then
Yes.
in this case, can we define GT as the compression of GU?
Yes. Yes. Absolutely. Yes. 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 Actually, yes. The function, if the functions of unitary operators are the compressions of the functions of contractions are compressions. The compressions of the functions of the unitary dilation. Yes. And actually, the same can be said about the semispectral measure. The semispectral measure of a contraction actually is the compression of the spectral measure of the unitary dilation. Yes,
that
yes,
means,
you're
sir,
right.
that means, sir, there will be no need to take analytic bounded function, right? We can take any L infinitive or any measurable function for defining the functional calculus.
Yes, but if you consider not L infinity, because the semispectral measures is not necessarily absolutely continuous, but it is for all continuous functions. Yes, but in this case the calculus is not multiplicative. If you consider functions in the disk algebra, then the calculus is multiplicative. But you can define for arbitrary continuous functions, but it's not multiplicative.
Okay, sir. And so if we just if we ignore the multiplicity property, if we just consider the continuous function and consider the functional calculus, still at that time we have the two-norm estimate, right?
Such a Ellipses step. I have to think about this. Thank you for the question.
That means that if we take any continuous function, say GB a continuous function, and we define GT as a compression of the GU, and then if we take two arbitrary contraction and they are differed by a Hilbert-Smith operator, at that time GT minus say GT1 minus GT0, the difference of their Hilbert-Smith norm is given by some constant times T1 minus T0 2 norm.
Yes, yeah, but the problem is the following: that if you consider unitary dilations,
yes,
then if you know that the norm of T1 minus T2 is small, it is not true that the norm of U1 minus U2 is small. It's more complicated than this.
Okay. And sir, what is the references for this maximal dissipative operator and their functional calculus?
Well, for the paper I was talking about is accepted for publication in Mathematische Nachrichten, but it's not yet published. And
in your paper that is called absolute continuity of spectral shift, at that paper I saw the functional calculus little bit for this maximal dissipative operator.
Yes.
And one more question, sir. Here you prove the Ellipses type estimate for maximal dissipative operator. So is this related to the Crane-Trace formula for maximal dissipative operator or maximal class for maximal dissipative operator?
Excuse me, could you please repeat slower?
Sir, here you prove Ellipses estimate for maximal dissipative operator. So
Yes.
for any P class, right? For any certain class, if we deferred by any certain class operator, then we get some Ellipses kind of estimate in your technique.
Okay, I understand the question. Okay, in the case of self-adjoint operators, if the difference belongs to the Schatten phenomenon class SP and P is greater than 1 and less than infinity, then Potapov and Sukachev proved the Ellipses type estimate for self-adjoint operators.
Right.
And also for unitary operators, but I'm not sure that they consider the case of dissipative operators. My guess is that this is true. This is true for arbitrary analytic Ellipses functions, but I'm not sure they consider the case of dissipative operators.
So
Professor Peller, I'm afraid that we need to wrap it up. We went over time, so maybe if you don't mind, maybe you can stay in Zoom for some time, and if people have questions, then you can answer them. But
Okay.
But other than that, we'll probably let's thank the speaker once again, and thank you very much. And we'll stop the recording. And if there are any questions, please stay in Zoom. I'll be here as well.
Okay.